Welcome to Notes 10.45. Today we are going to be talking about circles and the angles associated with them. And this is going to be fairly new to you, so make sure that you take good notes and work all the problems, and you should be in good shape. All right, let's begin, as always, with vocabulary. So we're going to talk about inscribed angles. Inscribed angles is any angle whose vertex is on the circle and whose sides contain chords of the circle. So let's see what that would look like. We start with our circle, and there's a circle, and then my vertex is going to be on the circle. So let's say this point right here is my vertex. There's one chord, and here's another chord. So this angle right here, that's my inscribed angle. Vertex on the circle, sides are chords of the circle. And if we have a vertex angle, if we have an inscribed angle, then we have an intercepted arc. The intercepted arc lies on the interior of the angle and has endpoints on the circle. So in this inscribed angle right here, this would be my intercepted arc. It's the arc that's on the interior of the angle. All right, and then we can have an inscribed polygon. We've talked about these before. So an inscribed polygon is a polygon with all vertices on a circle. We talked about it back in our triangle unit, specifically when we were talking about the circumcenter of the triangle. So let's see how this one works. So we have a circle, and then we have a polygon, and all of the vertices of my polygon are on my circle. All right, so that would be an example of an inscribed polygon. And if that is my inscribed polygon, then the circle that contains it is my circumscribed circle. So red is the inscribed polygon, black is the circumscribed circle. So one of the major goals of this unit is figuring out what measure angles have. And this theorem right here is one of the critical ones. And it states that the measure of an inscribed angle is 1/2 the measure of the intercepted arc. So the measure of angle ADB here, the measure of angle D, is going to be 1/2 of the measure of arc AB. Okay. Which means that vice versa, the measure of arc AB is going to be 2 times the measure of the inscribed angle. Okay, so either one of those is true. So if we look at angle S down here, right, the measure of this angle is going to be 1/2 the measure of the intercepted arc. Well, here's my intercepted arc. It's 60, so the measure of angle S is going to be 30 degrees. And then we have to find the measure of arc RQ. Well, we don't have an angle that intercepts RQ, but we do have this angle right here which intercepts QS. And if this is 37, then the measure of arc QS here is going to be twice that. So it's going to be 74 degrees. How does that help? Well, if I look at what's going on in my circle here, this whole thing right here is half a circle, right? Because it's the diameter cuts it into 2 congruent parts. So the whole thing is 180. So I just take 180 degrees and I subtract that 74 degrees, and I find out that the measure of arc RQ is 106 degrees. Pretty straightforward. Okay, and then we have a theorem that kind of naturally follows from the previous one, which states if we have 2 inscribed angles in a circle and they intercept the same arc, then the angles are congruent. So if I look at my circle over here, and I see that both angle D and angle C, they intersect arc AB, well then angle D is half of arc AB and angle C is half of arc AB. Therefore, they must be congruent to each other. So ADB must be congruent to ACB. Follows straight on. All right, moving on. Okay, so I want you to take the information that we've just learned on the previous page about my angle being 1/2 my intercepted arc, or my arc being twice my angle. or my angles being congruent to each other. And I want you to solve these problems here and then come back and check your answers once you've got them. So go ahead and do that and hit pause now. Okay, so you should have gotten 50 degrees for the first one, 80 degrees for the second one, and 31 degrees for the third one. If you don't understand why any of those are the case, please ask in class. Moving on. Okay, so here's a theorem that talks about what happens when we have a triangle inscribed in a circle. And it basically says if it's a right triangle inscribed in the circle, then the hypotenuse must be a diameter of the circle. And then the converse of that is if I've got a triangle inscribed in a circle and one side is diameter, then the triangle is a right triangle. And obviously the angle opposite the diameter is a right angle. So in my picture down here, I've got a triangle. One side of the triangle is a diameter of the circle, which means that angle B here must be 90 degrees. And it's 90 degrees if and only if AC is a diameter of the circle, which it is because it goes through the center of the circle. All right, and then here's one that students forget very quickly, but it's extremely important in this unit in both quizzes and tests. And it's that if I have a quadrilateral, it can be inscribed in a circle if and only if its opposite angles are supplementary. Okay, so quadrilateral inscribed in a circle if and only if, let me write this down. So the measure of angle D plus the measure of angle F equals 180, and the measure of angle E plus the measure of angle G equals 180. Okay, both pairs of opposite angles have to be supplementary. So that last theorem makes your life easy because it means that I have a quadrilateral inscribed in this circle, even though it doesn't really look like a circle to me. I don't know, maybe it's an optical illusion. So it means my opposite angles must be supplementary. So X must equal 92 degrees, and Y has to equal 80 degrees. This one works exactly the same way. I would like you to solve that for me in the notes check because it's pretty straightforward. Okay, so next theorem. And this theorem states if I have a tangent and a chord and they intersect on the circle, then the measure of the angle is 1/2 the measure of its intercepted arc. All right, so for my problem down here that I've got, or my diagram, the measure of angle 1 here, I've got a chord and a tangent. Okay, they intercept on the circle, so the measure of angle 1 equals 1/2 the measure of the intercepted arc, which will be arc AB. All right, there should be a little M right here. And then I can also, angle 2 also has its vertex, right? It's still part of that chord and tangent, so angle 2 is also 1/2 the measure of its intercepted arc, but this time its arc is ACB, it's a major arc. So measure of ACB. Okay, so both in our previous theorem, right, where we had a circle and then we had two chords, so circle and two chords, right, because my vertex was on the circle, my angle here was 1/2 the intercepted arc. Same thing here, on the circle, 1/2 the intercepted arc. Those two are related. Now this time I have two chords and they intersect inside the circle. So if that's the case, then the measure of each angle is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. Okay, so it's a little easier when you see it as a formula. The measure of angle 1 here is going to be 1/2 the sum, okay, so sum of the two intercepted arcs. So we're talking about the measure of arc AB and the measure of arc CD, okay, 1/2 of those two. And then angle 2 works the same way, except now we're talking about AD because it's one of the intercepted arcs, and BC is the other intercepted arc. So inside the circle, add the two arcs together, divide by 2. In this next theorem, we're talking about our two segments, and they can be a tangent and a secant, two tangents or two secants. The key is that they intersect outside the circle. Then the measure of the angle is 1/2 the difference of the measures of the intercepted arcs. So outside, we are talking about difference. That means subtract, and it's always the big arc minus the small arc. So for example, here I have a secant and a tangent. So the measure of angle 1 is 1/2 the big arc, which will be BC, minus the small arc, AC. Over here, I've got two tangents, and the measure of angle 2 is going to be 1/2 the bigger arc, PQR, minus the smaller arc, which is PR. So you'll notice that when I have two tangents, we're basically talking about the whole circle. Here, with my secant and my tangent, part of the circle, arc AB here, is left out. It's not included. But when I have two tangents, I'm basically talking about the whole circle. That's important to remember, because whatever this one is 360 minus that. Okay. And then finally, when I have two secants, the measure of angle 3 here is going to be 1/2 the bigger arc, XY, minus the smaller arc, WZ. So basically, inside, add, outside, subtract. All right, that's your little shorthand for remembering it. I think we're going to make a flip book of all this tomorrow anyway, so you'll get to do that then. All right, so let's use those theorems to solve some problems. So we need to find the value of x, and we've got chords that intersect inside the circle. Well, inside means add. So x is going to equal 1/2 the sum of my two intercepted arcs. So 112 plus 140, and that gets me 126 degrees. All right, now we have outside. Outside means subtract. So my angle is going to be equal to 1/2 the big arc, 170, minus the small arc, which is 72. So that gets me 49 degrees. And that's how those formulas work. But obviously it's not always that simple. So let's do a slightly more complicated problem. So you're flying in an airplane about 5 miles above the Earth, and we want to know the measure of arc BD here. Okay, the part of the Earth that you can see. So basically we want to know how many degrees that is. And there's a bunch of different ways you can tackle this problem. So why don't you take a moment, think about it, try to solve it, and then come back and check and see if we solve it the same way. Or if your way worked equally as well. If you got the same answer, you just went about it a different method. So go ahead, solve it, and then come back and check. Hit pause now. All right, so basically what we have going on here is we have two tangents. Okay, so you could apply the rule that the measure of angle C equals 1/2, and it's outside, so it's subtract, the measure of arc BED minus the measure of arc BD. And we can find angle C, and then we can solve this problem. Okay, that's totally doable, and it fits with all the stuff that we've been doing in class today, or in this notes today. However, there's actually an easier way to do it. Remember our old friend, the central angle. This is the one we haven't talked about today, but we've talked about angles inside the circle, we've talked about angles outside the circle, we've talked about angles on the circle. My last one is my angle at the center of the circle. So measure my central angle, measure central angle equals the measure of the intercepted arc. Okay, those two are equal. So if we can figure out what the central angle is, then we know what the measure of the intercepted arc is. So we're going to do it that way. Well, I can't figure out what angle A is, but I can certainly figure out what, for example, angle CAD is, because I have a right triangle, because what I can see is a tangent, right? If it just grazes what the plane can see on the Earth, then we're talking about a tangent. So that is a right triangle, and I know two of the sides, which means that I'm going to have to use my old friend trig. No matter how you did this, you needed to use trig. So if your solution did not use trig, then you probably did not do it right. All right, so let's use some trig. So I'm looking for the measure of this angle right here. Well, from the perspective of this angle, I have the adjacent and I have the hypotenuse. Adjacent and hypotenuse is cosine. So the cosine of angle CAD is equal to my adjacent, 4,000, over my hypotenuse, 4,005. So I'm looking for an angle, so the measure of angle CAD is going to be my inverse cosine of 4,000 divided by 4,005. And you do the math, and I think you get about, let me see, you get about 3 degrees. Okay, because we're going to round to the nearest degree because it doesn't make any sense to go more precise than that, which means that the measure of arc BD is equal to twice that, because angle A here is going to be 6 degrees, so the measure of arc BD is going to be 6 degrees. Did you get 6 degrees? If you did, great job. If not, and you still don't understand how I did, be sure you ask about it in class. All right, here we are on our last page, and we've got 4 questions we need answered. So I would like you to go ahead right now and do questions 1, 3, and 4. And then you can come back and check your answers for those with me. And then question number 2, you are going to answer in the notes check. All right, so go ahead and work 1, 3, and 4. When you've got answers, come back and check them. Hit pause now. All right, so in this first one, my arc is twice my angle. So 240 for that. In number 3, my angle is outside my circle. Therefore, my angle equals 1/2 the difference between the bigger y minus the smaller 30. And when you solve all this, you find out that y equals 82. And then in this one, I chose to make angle DEC. I called that x, just to kind of simplify things. And I had my adjacent, which was 4, and then my hypotenuse, which was 6, because if this part was 2 and the radius was 4, then altogether that's 6. So I did the inverse cosine, and I found out that that angle right there was 48, which meant that the whole angle AED was 96, which meant that this arc right here, arc AD, was 96. Well, if this part is 96 and the whole thing is 360, then I just subtract to find out what A is, and I get 264 degrees. All right, if you have any questions about any of the problems that I've covered today, be sure that you ask about them in class. Also, be sure to go on and do the notes check, and I will see you in class. Thanks.